binding energy of a nucleus. Let us say you have a nucleus consisting of number of nucleons. Suppose if you want to break this nucleus into individual nucleons, then some amount of energy is required for that. That energy is known as binding energy. On the other hand, let us say initially all the nucleons are separated by a large distance. Then you are trying to combine them together to form a nucleus. In such case, the same amount of energy released. This energy released in the formation of a nucleus is known as binding energy. For example, in the earlier case, we have got some mass defect for oxygen nucleus. How this binding energy comes into picture is, when a nucleus is formed, the actual mass of the nucleus is less than its theoretical mass. That is, when you take the sum of individual nucleons, that mass will be large when compared to the actual mass. The difference in this mass is converted into energy according to Einstein's mass energy relation, and that energy is known as binding energy. So you can say that binding energy is equal to mass defect multiplied by c square using E equal to mc square principle. So we can say that we can write binding energy as delta m, which is nothing but mass defect multiplied by c square. That is binding energy. That is how binding energy comes into picture in case of a nucleus. For example, in the earlier case, we have calculated mass defect of oxygen nucleus to be delta m. Mass defect of oxygen nucleus is 0.13691 atomic mass units. And this, if you convert into binding energy, see, generally one atomic mass unit when converted into energy is about 931 million electron volt. So if you convert this mass defect 0.13691 into energy, that comes out to be 0.13691 multiplied by 931. That gives you 127.5 million electron volts. This is what we call binding energy of the oxygen nucleus, which is equal to 127.5 million electron volts. How we got that one is, we have taken mass defect of the oxygen nucleus multiplied with c square, you got the value of that much. That is the mass defect in case of, that is the binding energy in case of oxygen nucleus. The binding energy per nucleon plays an important role in case of a nucleus and nuclear reactions. For example, if binding energy of a nucleus is represented by Be, then let us say that for a nucleon, the number of nucleons is represented by A, where A stands for the mass number. So the total number of nucleons is A. If you divide binding energy by the number of nucleons within the nucleus, we will get binding energy per nucleon. So this binding energy per nucleon varies from one nucleus to other nucleus. Like if you plot a graph between the mass number of a nucleus and binding energy per nucleon, then we'll get a graph looks something like this. On x-axis, we'll take mass number A, and on y-axis, we are using binding energy per nucleon. It is in million electron volt. So the graph looks something like this. As you can see, for a very small mass number nuclei, its value is less, and then it increases very sharply and reaches to a maximum value. Beyond that, it remains constant, fairly constant for a limited number of nuclei, and beyond that one it gradually decreases. Generally it is observed that when the mass number A is between 30 and 30 to 170, that is the nuclei with mass numbers 30 to 170, this binding energy per nucleon fairly remains constant. And also if the mass number is less than 30 or if the mass number is greater than 170, then the binding energy per nucleon gradually decreases. In fact, it reaches a maximum value of 8.75 million electron volt. In case of Fe, that's the maximum possible value, and you see it implies that there are certain nuclei which requires a less binding energy. That is, when you want to dismantle that particular nucleus into individual nucleons, you require lesser energy, and there are certain nuclei which require a very high energy to split into separate nucleons. When a heavy nucleus with a lesser value of binding energy splits into two smaller nuclei for which the binding energy is more, then obviously an amount of energy is released. That's a nuclear reaction called nuclear fission. A heavy nucleus splits into two smaller fragments and releasing energy. Similarly, a very light nuclei with lesser binding energy combines together to form a higher value of nucleus, that is a heavy nucleus, relatively heavy nucleus. Again, binding energy is large. It implies that energy is released during that process also. That comes in nuclear fusion, another reaction. Two lighter nucleus joining to form a heavy nucleus is called nuclear fusion. Again, amount of energy is released in that process also.